What are the chances of two stars bursting into view visible to the unaided eye? Enormous tremors ripping apart the foundations of Venezuela, and the notorious three-eye Atlas getting grazed by a solar flare all crammed into a 72-hour span. If this were a film plot, producers would toss it out for being way too contrived. Yet, here we are in the real world. And reality has just staged the most impeccably timed celestial spectacle in contemporary stargazing annals. Following these occurrences, even the biggest skeptics are beginning to question whether this is mere luck or something eerily more profound. This evening, we'll break down every incident with meticulous detail, explore the mechanics of stellar outbursts and earthly upheavals, and then step into the uneasy realm where random events hint at deeper designs. Stick around to the finish, as our findings on September 2025 could upend all our assumptions about the cosmic drama unfolding above. Part 1. A wild sequence of happenings, twin stellar blasts, twin colossal quakes shattering the terrain under Venezuela, and a cosmic wanderer brushed by a coronal mass ejection. Everything unfolding mere days apart in the closing days of September 2025. If the cosmos feels like it's sending a message, trust me, plenty of folks sense it too. Let's chart this stellar smash-up of incidents step by step. Astronomers spotted V1935 Centauri on September 23rd, a nova igniting in the southern sky's Centaurus grouping, flaring up to a magnitude of 5.8, bright enough for backyard stargazers. Not long after, a second cosmic flare-up made its debut. V9994, Sagittarius ignited in the Sagittarius Bowman, hitting magnitude 6.2. Suddenly, two stars were out there, plain as day for anyone who bothered to glance skyward. At the same time, some 7,000 miles from the closest telescope outpost, our planet was stealing the spotlight. On September 24th at 2221 UTC, a 6.2 magnitude shaker hit 24 kilometers east-northeast of Men Grande in Venezuela's Zulia region, starting just 7.8 kilometers underground. It rattled both Venezuela and neighboring Colombia. But the planet had more in store. A few hours on, at 0351 UTC on September 25th, another jolt A6.3 magnitude tore through the identical area, this one from 14 kilometer deep. Paired stellar flares, paired seismic shocks, and up high, beyond casual sight but caught by orbital watchers, another drama was brewing. Experts at NOAA's Space Weather Prediction Center were eyeing coronal mass ejections, those massive billion-ton blobs of charged solar particles flung out at over 1 million miles per hour. Their simulations indicated these sunblasts were intersecting with an extraordinary anomaly. Three-eye Atlas, the third verified outsider to cruise through our solar system. This is where the schedule turns downright dramatic in its alignment. The nova sightings and Venezuelan rumbles bunched up from September 23rd to 25th. Projections for the CMEs peaked right in that slot, and Three-Eye Atlas, uncovered only 2 months prior by the Asteroid Terrestrial Impact Last Alert System, was slicing through the solar system's core amid what could be the height of Solar Cycle 25's frenzy. These incidents stretch across distances that boggle the mind. The novas popped in Centaurus and Sagittarius, star patterns mostly seen from the planet's southern reaches, their glow having journeyed light years to hit us bang in this extraordinary stretch. The quakes hammered northwest Venezuela near Men Grande, in a hot spot where the Caribbean plate scrapes relentlessly against its South American counterpart. The coronal mass ejection swept across the inner heliosphere, a vast zone dwarfing Jupiter's path. Meanwhile, Three-Eye Atlas was slicing the ecliptic, that flat plane of the solar system where planets mostly play slipping between Mars and the Sun. We're not suggesting some direct link tying them together. Jumping to conclusions right now would be hasty and potentially unwise. Our approach involves charting the anomaly cluster, recording the alignment of events, and getting ready to balance established scientific interpretations with bolder theoretical ideas. The United States Geological Survey has found no proven link between solar activity and seismic events. Experts in solar physics point out that coronal mass ejections are common occurrences during periods of heightened solar activity. Astronomers studying stars view novae as foreseeable yet erratic outcomes of interactions between paired stars. Yet what sets this particular week apart in contemporary astronomical records is truly remarkable. 3I Atlas marks just the third verified interstellar object spotted to date, coming after Oumuamua in 2017 and 2I Borisov in 2019. Even more captivating, this could be the initial instance of observing an interstellar traveler exposed to fierce solar conditions around the peak of solar maximum. We already know the effects that CMEs can have on comets within our solar system. Back in 2007, ESA's Stereo spacecraft captured footage of a coronal mass ejection that essentially ripped away the ion tail from Comet Encke, an incident highlighting the harsh dynamics of space weather encounters. The implications for the months ahead go well beyond mere scholarly interest. 3I Atlas is set for a close pass by Mars on October 3rd, coming within 19 astronomical units, about 28 million kilometers from the planet. Orbiters around Mars, such as ESA's ExoMars and NASA's Mars Reconnaissance Orbiter, are gearing up for impromptu scans that might reveal fine details of the interstellar object's core and surrounding envelope with exceptional clarity by the end of October. On October 29th, in particular, 3I Atlas will hit perihelion, its nearest point to the Sun at 136 astronomical units. That's still beyond Earth's path, but near enough for Earth-based observatories to examine its makeup and dynamics live. The alignment for viewing improves further on December 19th, when 3I Atlas swings to its minimum distance from Earth at 1.8 astronomical units. To put it in perspective, that's nearer than Mars gets at opposition, providing extended windows for monitoring by both major facilities and backyard stargazers using basic scopes. This overlap happens amid a time of year when solar influences often ramp up. The fall equinox sparks the so-called Russell-McFerrin effect, a peculiar alignment in Earth's magnetosphere that boosts interactions between the planet's field and incoming solar wind fluctuations. From September to November, we typically see some of the most dazzling northern lights and the strongest disruptions from space weather on our tech infrastructure. Here's our commitment to you. We'll present straightforward scientific accounts alongside daring hypothetical explorations, always marking them distinctly. It's important for you to distinguish between what's backed by direct evidence, what's grounded in theory but unproven, and what's pure conjecture. The evidence counts. The awe counts. And at times, the truest statement from science is simply, we're not sure yet, but we're keeping a close eye. As we explore further, ponder this. If solar eruptions can shear off the tails of comets that have circled our sun for ages, what could they inflict on a body that's journeyed millions of years across the void, laden with frozen volatiles and particles born in a foreign star system? The answer is coming soon. Up next, we'll look at those abrupt stellar blasts, the paired novae that illuminated the southern hemisphere right as tremors stirred beneath our feet. Part 2. The paired novae, abrupt bursts in the southern skies. In the early morning darkness of September 23, 2025, hobbyist stargazer John Seitch was following his long-standing routine, surveying the southern constellations from his setup on Chatsworth Island in New South Wales in search of cosmic outbursts. The discovery he made that dawn would quickly draw the focus of gamma-ray observatories and X-ray instruments worldwide. The solar system welcomed V1935 Centauri not through grand announcements, but via bursts of light. An early observation by Seitch revealed a star in the Centaurus constellation that hadn't shone brightly enough to catch attention previously, hitting magnitude 5.8, just visible to sharp-sighted skywatchers in remote dark spots without aid from binoculars. Yet, this wasn't a typical flare-up. Soon after Seitch's alert hit the Central Bureau for Astronomical Telegrams, orbital telescopes zeroed in on an astonishing phenomenon. NASA's Fermi Gamma Ray Observatory activated, capturing intense high-energy photons pouring from the nova's location. The Swift satellite, built to detect gamma-ray bursts, redirected its X-ray instrument toward Centaurus and started logging robust X-ray outputs, clear indicators of fierce particle speeding in the nova's outward-rushing shock front. These went far beyond mere spectacles for amateur astronomers. They pointed to physics pushed to its limits, electrons and protons whipped up to nearly the velocity of light, magnetic fields contorted into tangles, and heat levels climbing to millions of degrees. But V1935 Centauri had more surprises in store. Mere days afterward, the universe struck once more with V799D. Sagittarius exploding in the adjacent Sagittarius constellation, peaking at magnitude 6. 2 upon detection. 2 stellar blasts, both spotted by the same vigilant observer, both accessible via modest telescopes or binoculars, all crammed into one extraordinary week. What stunned expert astronomers about this duo? Novae aren't all that scarce. Our galaxy sees roughly 10 to 12 annually, but witnessing 2 escalate to near visible by eye brilliance in such quick succession is truly rare. The previous instance of dual bright novae visible at once dates back to the summer of 2023, with earlier parallels stretching years further into the past. The science driving these blasts unfolds a tale of cosmic feeding frenzies spanning eons. Every nova starts with a white dwarf, the compact, scorching remnant of a deceased star, Earth-sized yet packing the sun's mass. This stellar corpse orbits alongside an ordinary star, siphoning hydrogen bit by bit from its partner's outer layers. Over years, centuries, or even millennia, that gas piles up on the white dwarf's exterior, compressing and heating under gravity's crush until it hits a tipping point. Then, the gathered hydrogen sparks uncontrolled runaway nuclear fusion, not the steady glow sustaining active stars, but a detonating inferno that can amplify the binary pair's luminosity by 10,000 times or greater. The blast spares the white dwarf itself, merely stripping off its outer shell and resetting the slow buildup cycle. Certain novae cycle back on regular intervals, flaring every few decades, while others lie dormant for thousands of years between events. V1935. Centauri's gamma-ray and hard X-ray signals expose the outburst's fiercest traits. As the nuclear blast hurls debris outward at thousands of kilometers per second, it generates shock waves that propel particles to immense velocities. These speedy particles clash with magnetic fields and nearby material, generating the potent photons that set off Fermi and Swift. This mirrors the mechanisms at work in supernova debris fields and energetic galaxy cores, natural engines, converting everyday stuff into blazing radiation. For skywatchers in the southern hemisphere, both novae command excellent observation spots. V1935 Centauri lies deep south of the celestial equator, posing a tough mark for northern hemisphere viewers who can only glimpse it briefly as it climbs their southern skyline. V79994 Sagittarius, nestled in the Archer's realm, offers a comparable southern slant, hugging low on the southern horizon for those in moderate northern latitudes. Observers in northern latitudes might miss it, but for those below the equator, it's soaring prominently across the heavens. The way this discovery unfolded highlights the teamwork central to today's study of fleeting celestial events. Reports from SECH, shared via the International Astronomical Union Central Bureau, sparked a wave of subsequent checks. Circular 5611 verified the spotting of V1935 Centauri, whereas 5612 recorded V79994 Sagittarius. In just a few days, facilities globally were capturing light measurements, accurate luminosity readings, and spectral data that exposed telltale emission signatures from hydrogen, helium, and denser elements within the growing nova envelopes. Enthusiast stargazers contribute vitally to nova research via groups such as the American Association of Variable Star Observers. Their regular evening watches deliver the detailed timing needed to track the development of nova brightness profiles, the intricate sequences of surges, steady intervals, and slow fades that hold insights into the blast dynamics and the traits of the paired star systems. While pro-grade scopes can't watch every nova around the clock, committed hobbyists keep tabs on luminosity shifts evening after evening, supplying info that refines our grasp of these cosmic blasts. The system for labeling often baffles those new to the field. V1935 Centauri earned its label as the 1935th variable officially catalogued in the Centaurus constellation, and V7994 Sagittarius as the 7994th in Sagittarius. These lasting identifiers supersede the provisional tags given at first sighting, which occasionally leads to timeline mix-ups since later found items might get lower numbers from bureaucratic holdups. Both novae should dim steadily in the weeks and months ahead, adhering to the standard nova fade-out that stretches from months to years. That said, their progression could hold unexpected twists. Certain novae experience dust-building phases weeks post-outburst, causing a brief drop in visibility as fresh dust particles block and redirect the nova's glow. Others display elaborate multi-peaked brightness patterns as varying mechanisms take the lead at different stages. Space weather fans inevitably wonder if these starbursts, hitting the same week as notable magnetic disturbances on Earth, signal anything beyond chance. Mainstream experts in astronomy offer a straightforward no. Novae in nearby star patterns, sitting thousands of light-years away, present zero immediate risk to our world and cast no detectable effect on local events. The power from these blasts, immense on a human scale, spreads thin over immense cosmic voids, reaching us merely as a soft uptick in light particles, stunning to behold, safe to witness. Still, the alignment seems striking. Paired stellar detonations amid a week of dual quakes, with a far-off comet weaving past amid lively sunspot action. The fairest reply might be to honor both the facts and the alignment, value the mechanics while staying receptive to how the cosmos sometimes aligns in manners that nudge happenstance toward poetic resonance. At the same time, 7,000 meters under any setup able to spot these starry displays, the firm ground in Venezuela was set to prove that detonations aren't exclusive to remote stars. Part 3. The Venezuela quakes, exactly at 22 hours, 21 minutes, and 55 seconds UTC on September 24th, the ground under Venezuela's Zulia state unleashed force matching multiple atomic blasts. The 6.2 magnitude tremor hit 24 km east-northeast of Mexique, stemming from a fairly shallow 7.8 km depth near enough to the surface to rattle structures in two countries. The shaking pulses spread out at about 6 kilometers. Seismic waves propagated swiftly through the bedrock, hitting inhabited zones mere moments after the initial break. Spanning from Marbo to Caracas and extending to border communities in Colombia and urban centers along the Caribbean shore, countless individuals sensed the earth shifting under them. Online platforms buzzed with footage showing oscillating light fixtures, vibrating panes, and locals fleeing structures amid urgent safety measures activating throughout the area. Yet the planet had more in store. Merely 5.5 hours afterward, at 39 UTC on September 25th, another substantial fracture hit almost the identical spot. On this occasion, the 6.3 magnitude tremor began at a depth of 14 kilometers deeper than the prior one, yet sufficiently near the surface to provoke severe ground motion. Its focal point lay roughly 27 to 28 kilometers east, northeast of Menegrand, aligning closely with the rupture area of the earlier quake. To appreciate the significance of these paired tremors, it's essential to comprehend the logarithmic basis of magnitude measurements for earthquakes. Specifically, a 6.3 magnitude quake unleashes about double the power of a 6.2. Together, these fractures unleashed force comparable to 1.6.4 to 6.5 magnitude event, a substantial outpouring by worldwide benchmarks. The incidents on September 24th and 25th marked the most intense shaking in the vicinity since the 7.8 magnitude Kamchatka quake on September 18th, ranking Venezuela's dual events as key seismic occurrences globally in late September 2025. The ensuing aftershocks added their share of tension. Later that day on September 25th, UTC, a 5.8 magnitude jolt impacted the same territory, adhering to the standard Omori decay trend that experts anticipate post-major breaks. Although a 5.8 may seem tame next to the primary shocks, it remains potent enough to inflict further harm and heighten unease in communities already rattled by the duo of big quakes. The local plate dynamics reveal the reasons behind such formidable seismic activity here. The Morocco Basin occupies an intricate region where the Caribbean plate rubs against the South American plate, forming an array of fault networks that encompass the Bocano fault system and the UK Anand-Santa Marta fault trends. These structural edges have built up strain over years, decades, or even centuries, amassing power that inevitably erupts via abrupt shifts earthquakes. The variation in depths for the primary pair, 8 km against 14 km, plays a crucial role in the strength of surface vibrations. Quakes closer to the surface generally yield greater acceleration at ground level than those farther down with equal magnitude, as the waves travel a shorter path with fewer chances to dissipate. The shallower origin of the September 24th event probably fueled the broad accounts of vigorous tremors felt throughout Venezuela and Colombia. Various monitoring bodies issued marginally divergent magnitude estimates for these occurrences, underscoring the intricacies involved in assessing quakes. The United States Geological Survey first pegged the initial one at 6.2, whereas the European Mediterranean Seismological Center and additional global observatories offered figures from 6.1 to 6.3. Such variances stem from multiple influences, including diverse analytical approaches, refinements with incoming data from more sensors, and variations among moment magnitude, surface wave magnitude, and body wave magnitude computations. The societal toll of these tremors reached well past mere data points in seismology. Directives to evacuate impacted thousands of inhabitants, especially those in taller edifices that endured extended rocking. Rescue squads deployed widely, evaluating structural harm and verifying the functionality of vital facilities like medical centers, overpasses, and energy facilities. Although preliminary assessments, despite the earthquake's intensities suggesting only modest structural harm, evaluation crews persisted in their inspections for several days following the incidents, recording evident destruction alongside possible enduring vulnerabilities in buildings. This area has long been prone to substantial seismic events. The intricate geological setup near Lake Marico and along the extensive Caribbean-South American plate margin produces frequent tremor series. While quakes of such strength happen sporadically, historical data shows that substantial breaks here occasionally spark further motion on surrounding fault lines. This happens through a mechanism known as stress transfer, where one seismic event alters the pressure on neighboring fault networks. The sequence of these occurrences sparked inquiries from experts in seismology and everyday people alike. Might more powerful tremors come next? The probabilistic response is complex. Sequences of aftershocks are anticipated and typical, with the strongest ones usually striking in the days or weeks right after the primary quake. That said, experts in earthquakes can't accurately forecast if a bigger one could hit the area soon. Forecasting seismic events stays challenging, even after years of studies on warning signs, buildup of tension, and predictive models based on data. Worldwide observation systems followed each aftershock closely, assembling insights into the fault network's reaction to the pressure shifts from the pair of significant breaks. The International Centroid Moment Tensor Catalog started generating in-depth reviews of the fault angles, sliding motions, and break patterns for each quake. Such details assisted specialists in grasping which parts of the faults shifted and how the overall pressure landscape evolved in the wider zone. To those living in Zulia State and adjacent regions, these paired earthquakes served as a sharp alert to the area's tectonic truth. Standards for building, readiness for crises, and local alert mechanisms all get challenged in moments like these. The fairly contained reports of harm, considering the quake's strengths, probably stem from lucky circumstances. The shakes happened when folks were mostly indoors instead of in riskier office or factory settings, plus recent advances in building practices and crisis management skills. A larger issue arising from these happenings concerns their alignment with other occurrences in that extraordinary 7-day span. Earthquake researchers insist there's no established link tying sun flares, cosmic conditions, or celestial happenings to tremor triggers. The United States Geological Survey's stance highlights that any ties between space conditions and ground shakes lack solid evidence, regardless of recurring suggestions in academic papers and news outlets. Still, people instinctively look for links, particularly when striking incidents bunch up temporally, paired novas, paired quakes, lively solar conditions, and a cosmic traveler passing close to the Sun's core. The overlap seems meaningful, though the underlying processes are still murky. The fairest scientific stance might be to record the sequence, examine each event on its own, and stay receptive to finding ties without jumping to cause and effect from mere coincidence. While tremors kept unsettling Venezuela's awareness, the Sun geared up to show that our planet's close cosmic surroundings could match the drama of its own rocky crust. Part 4. The Sun Fires. 93 million miles over Venezuela's trembling terrain, our central star orchestrated its fiery performance. In those very days when cosmic blasts illuminated southern hemispheres and quakes split South American foundations, the Sun released coronal mass ejections, massive billion-ton plumes of charged plasma. Plasma capable of intersecting with an extraordinary phenomenon in human history, an interstellar object. Coronal mass ejections stand out as among the most intense occurrences within our solar system. These outbursts originate in the Sun's corona, where magnetic field lines become twisted, knotted, and ultimately break apart like overstretched elastic bands. Once magnetic reconnection takes place, it unleashes energy on the scale of billions of hydrogen bombs, propelling plasma at velocities ranging from 250 to 3,000 km swift enough to cover the distance from the Sun to Earth in just 1 to 4 days. NASA's Space Weather Prediction Center monitors these solar disturbances via the WSAE-NLI model, an advanced computational tool that simulates the movement of coronal mass ejections across the heliosphere. This system accounts for solar wind velocity, density levels, and magnetic field directions to predict the timing and locations where these plasma formations might encounter satellites, planets, and various bodies along their route. In late September 2025, Enlil predictions indicated heightened activity, with several CME incidents weaving through the inner solar system on the very days that delivered twin novae and the paired seismic events. Yet, this narrative takes a groundbreaking turn. For the first instance in documented human records, one such solar eruption was headed straight toward an entity originating from beyond our star system. 3 Atlas, identified merely 2 months prior by the Asteroid Terrestrial Impact Last Alert System, was navigating the inner heliosphere amid the peak turbulence of solar cycle 25. This interstellar traveler, tracing a backward path tilted approximately 175 relative to the ecliptic plane, was passing through the orbital zone of Earth, a hotspot for solar weather interactions. Historical examples exist for the effects of coronal mass ejections on comets. The effects are no mere theory. They constitute established science, recorded by probes and detailed in scholarly publications. Back in 2007, the European Space Agency's Stereo spacecraft captured footage of a CME slicing off the ion tail of Comet Encke entirely. That separation, which persisted for hours, highlighted the fierce dynamics of magnetic reconnection between solar plasma and cometary substances. Comet tails develop via 2 separate mechanisms, each reacting uniquely to solar forces. Dust tails arc elegantly from the Sun, driven by radiation pressure, the steady yet subtle push of sunlight on tiny particles. Ion tails, however, extend rigidly outward from our star, aligned with the magnetic structures carried by the solar wind. Should a coronal mass ejection interrupt these links, ion tails may fully detach, wander from the comet, and fade as replacements emerge from newly exposed material. The assertion that 3 Atlas grazed by a CME draws from trajectory simulations rather than eyewitness accounts. Enlil projections indicated that the solar storm routes would overlap with the interstellar object's location in late September, though honesty demands acknowledging the limitations. While space weather simulations shine in outlining broad patterns, they falter on precise particulars. Thus, the encounter qualifies as a projected possibility, not a confirmed finding in scientific journals. Assuming the models proved accurate and the clash happened, various detectable outcomes could arise. Heightened ionization might illuminate the visitor's coma, the hazy envelope of gas and dust encircling its core. Alterations in the ion tail's shape could show up in telescope views, as magnetic interruptions reshape the flow of charged particles departing the body. Spectral data might uncover molecular traces with solar radiation freeing compounds such as CN, CO, and CO2 from the object's primordial ices. Enthusiast observers around the globe stood ready to capture any such transformations. The worldwide global community of comet watchers, linked via digital discussion boards and astronomy groups, keeps a close eye on captivating celestial bodies each night. By examining their photos over periods, they uncover faint shifts in luminosity, tail configurations, and coma shapes that typically go unnoticed by pro-telescopes zeroed in on different priorities. The science behind coronal mass ejections clashing with comets hinges on magnetic reconnection, the very mechanism sparking solar flares and auroral disturbances. As sun-derived plasma, laden with knotted magnetic lines, brushes against a comet's ionized layer, those lines may link up, break apart, and reform, unleashing power that speeds up ions and sparks visible effects. It's a beautifully intricate process. Magnetic configurations shift live, transforming pent-up magnetic power into motion for electrified bits. 3I Atlas stands out as far more than a routine spot for solar outbursts. As the third verified extrasolar visitor following Arama in 2017 and Boris in 2019, it hauls substances born near some distant sun in another cosmic setup, possibly eons in the past. Should solar tempests tweak its path, this marks the inaugural recorded instance of our star meddling with stuff from a foreign stellar domain. The path of this intruder heightens the odds of such encounters compared to its predecessors. In contrast to Oumuamua, which zipped through the Sun's core zone at a steep angle to the orbital flatland, 3I Atlas traces a route hugging the ecliptic, the disk where solar bursts cluster and where our planet bears the brunt of cosmic weather hits. Solar Cycle 25 has set a lively stage for these clashes. The 11-year rhythm hit its peak stretch in 2024 and 2025, yielding higher sunspot counts, more flare outbursts, and a surge in plasma blobs hurled from the corona. This schedule exposes 3I Atlas to our sun in its feistiest mood, enduring space weather barrages that earlier wanderers dodged. Confirming these ejection encounters demands meticulous review of light fluctuations, spectral shifts, and form alterations across spans from hours to days. Top-tier scopes and hobbyist stargazers around the globe tracked 3I Atlas into late September, yet early findings stayed tentative pending deeper scrutiny. The broader fallout stretches past this one occurrence. By recording how our sun reshapes alien debris, we unlock clues to parallel dynamics across the Milky Way. Presumably, rival suns fire off their own plasma blasts, which could reshape drifters weaving through their realms. 3I Atlas could bear traces of brushes with prior star clusters from its long haul across the void. As September 2025 wrapped up, a pileup of happening star blasts, ground shakers, sunfits, and outsider meddlings wove a narrative that upended easy notions of random sky events. Were these isolated bursts bunching up by luck, or did a deeper pattern lurk? Clarity would come as 3I Atlas pressed onto its Mars skim on October 3rd, bearing any tweaks from our sun's plasma volleys on this far-flung Voyager. Part 5. Weirdness Framed. Pause and reflect on the landscape we've sketched, paired star detonations plain to the unaided gaze. Paired 6. Zero quakes tearing open mere hours apart, plasma ropes lancing the sun's heart, and an extrasolar guest slicing our turf amid peak solar frenzy. An immense cosmic rush packed tight. As we entered the closing days of September 2020, the fifth instance unfolded. Here, genuine scientific inquiry intersects with our innate ability to spot patterns in the world around us. And that intersection isn't always easy to navigate. Human minds develop to pick up on important links amid chaotic settings, the faint noise that could warn of danger, a shape in the sky hinting at incoming weather, shifts in behavior, signaling potential risks or chances in social dynamics. This mental framework proves useful in numerous situations, yet it sometimes tricks us into seeing importance in random groupings. Mainstream experts provide straightforward insights into these occurrences. The United States Geological Survey states there is no proven link between space weather effects and earthquakes. Years of research examining correlations have not uncovered dependable ways to forecast quakes using solar patterns or seismic activity. Seasoned earthquake specialists stress that predicting tremors is still beyond our reach with today's tools, regardless of whether they draw from ground-based signs or forces from beyond Earth. In the same vein, astronomers who focus on stars see novae as expected outcomes of how paired stars develop, happening when a white dwarf gathers enough matter from its partner to spark an uncontrolled nuclear reaction. These stellar blasts align with the laws of star physics rather than anything tied to our planet or the broader solar setup. V1935, Centauri and V7994, Sagittari, stand as typical, though striking to the eye, cases of galactic processes that happen routinely. Experts on the Sun examine coronal mass ejections as inevitable results of how magnetic fields change in the Sun's outer atmosphere. Such incidents ramp up in frequency near the peak of the Sun's activity cycle, positioning late 2025 as a probable period for several of these ejections. Scientists have thoroughly recorded how solar disturbances interact with comet substances, viewing it as standard behavior in charged particle physics instead of anything unusual. Still, recognizing these established views doesn't mean we have to downplay the striking alignment of these timings. Occasionally, the cosmos aligns in patterns that push mere chance toward a sense of meaningful coincidence. Though the core reasons might be ordinary, the real challenge is balancing sharp doubt with fitting awe. In our ongoing examination, we'll draw firm lines between various kinds of assertions. We'll start with solid observations, quake strengths, site positions, light spectrum readings, and detection records. These form the bedrock: what devices captured, what orbiting tech picked up, what ground sensors gauged. On top of that, we'll add levels of analysis rooted in proven physical principles and reliable simulations. Stepping further into guesswork, we'll proceed with caution and explicit warnings. Tentative ties between sun flares and Earth-based happenings, conceivable effects from star events on our solar neighborhood, imagined pathways connecting space-scale and Earth-shaking forces. These ideas merit consideration as long as we clearly mark them as unproven ideas, not settled truths. For everyday readers, we need to clarify terms related to space happenings. A nova is a sudden stellar outburst that amplifies the glow of a two-star setup by thousands or even millions of times, triggered by a runaway nuclear fusion on the surface of a white dwarf. It stands apart from a supernova, which obliterates the star involved. A coronal mass ejection involves massive clouds of plasma weighing billions of tons, hurled from the sun at velocities ranging from hundreds to thousands of kilometers per second. Perihelion refers to the nearest point in an object's path to the sun. One astronomical unit is the typical gap between Earth and the sun, about 93 million miles or 150 million kilometers. Ion tails develop as the solar wind yanks electrons away from gas particles in a comet's structure. The comet's coma generates charged particles that align with magnetic field lines and stream directly outward from the sun. These tails stretch across millions of kilometers in space, offering tangible signs of unseen magnetic forces at work among stars and lesser celestial objects. In the upcoming exploration, we'll distinguish real observations from speculative links, all while honoring both rigorous science and our innate sense of wonder. Our analysis will delve into the intricate mechanics of star blasts, seismic breaks, and solar flare dynamics. We'll follow 3I Atlas during its Mars close approach on October 3rd and its nearest solar pass on October 29th. We'll review sound scientific ideas linking space events to Earth-based occurrences, paired with explicitly marked ideas on wilder scenarios. The fall equinox period often boosts space weather impacts via the Russell-McFerrin effect, which links Earth's magnetosphere to solar wind patterns and typically heightens geomagnetic disturbances in September and October. Such yearly boosts offer key background on why late September could see heightened space weather on its own, without ties to unrelated events. 3I Atlas presents exceptional research chances exactly as our third verified interstellar object, and the initial one spotted amid intense solar activity. Its path's alignment close to the ecliptic, where much of the solar system's action clusters, boosts the odds for diverse mission views and space weather engagements. In contrast to Oumuamua, which sped off too fast for thorough examination, or Borisov, which stayed fairly remote, 3I Atlas allows prolonged viewing windows over multiple months. The implications for October and November go further than scholarly pursuits. Orbiters around Mars, such as ESA's ExoMars Trace Gas Orbiter and NASA's Mars Reconnaissance Orbiter, have scheduled chance observations for the October 3rd pass, which might yield groundbreaking high-detail images of an interstellar object's core and surrounding envelope. Telescopes on the ground across the globe keep tabs on shifts in luminosity, spectral shifts, and shape alterations that may show solar conditions influencing extraterrestrial substances. Regarding seismic oversight in Venezuela, aftershocks usually persist for weeks or months after big quakes. Though experts can't forecast if bigger shakes will hit, they sustain ongoing surveillance of local tremors and stress buildup. The intricate plate interactions at the Caribbean-South American margin guarantee ongoing quake production in the area, even if exact moments stay impossible to foresee. Our approach centers on sharing varied viewpoints transparently. Core scientific accounts warrant top focus since they build on solid principles and vast data. Out there theories merit a look, as long as they're kept separate from verified facts. People's drive to spot significance in seeming coincidences warrants acknowledgement, particularly when proof falls short on direct causes. Maybe the standout feature of this overlap is the moment. We're the pioneer era in history, equipped to spot interstellar travelers, watch worldwide quakes live, scan starbursts over the full light spectrum, and follow solar weather system-wide. Folks from earlier times could have seen vivid novae or endured quake jolts, yet they lacked the tools to link those to solar outbursts or space intruders, as such detection tech simply wasn't available. This effort will differentiate seen realities from mere suppositions, distinguishing between the imagined and the verified, the probable and the merely possible, is essential. Thus, how exactly do stars erupt without obliterating themselves completely? The explanation uncovers physical principles at scales that defy everyday human understanding. Part 6 delves into the structure of a nova. Envision a white dwarf, a compact orb about Earth's diameter, yet packing the mass of our whole sun. Its gravitational pull compresses substances to densities nearly 1,000,000 times greater than water. Surface heat lingers near 50,000 F. This celestial remnant is the leftover core from a star akin to our Sun. Once it depletes its nuclear resources, discards its outer envelope, and implodes into a ball of exotic degenerate material where atomic structures behave in ways unimaginable on our planet. Now consider this stellar inferno paired in a gravitational orbit with an ordinary star, maybe a red giant whose atmosphere has ballooned enormously in its old age. The white dwarf's pull slowly siphons hydrogen from the companion's bloated outer layers, drawing the gas across the interstellar void in twisting streams that whirl inward, much like liquid swirling down a sink. This pilfered substance builds up on the white dwarf's exterior, becoming thicker and more intense under intense gravitational squeeze. Over spans of decades, centuries, or even millennia, the hydrogen layer thickens. Heat and pressure rise progressively as additional matter layers onto the dwarf's surface. In contrast to the steady fusion in a star's heart, this buildup leads to a violent outburst. Once temperatures hit about 100 million Kelvin, uncontrolled thermonuclear reactions ignite. The blast-forming V1935 century unfolds in mere seconds. The runaway fusion devours the gathered hydrogen shell in a fierce blaze, unleashing power comparable to our sun's entire emission across thousands of years. Yet, the key distinction from a supernova lies here. The white dwarf endures. The detonation ejects just the thin outer layer of acquired material, sparing the core stellar husk to potentially restart the cycle. That's precisely why V1935 century's intense emissions drew scrutiny from global space telescopes. When NASA's Fermi Gamma Ray Observatory picked up gamma radiation from the nova's location, it captured signs of particles hurled to nearly light-speed velocities amid the blast's shock boundaries. Meanwhile, the Swift Observatory's intense X-ray readings exposed electrons twisting through potent magnetic zones at vast energies, generating synchrotron emissions spanning the full spectrum of light. Such extreme processes elevate novae beyond mere flares into vast natural particle boosters. The outward rushing envelope of expelled debris, hurtling at velocities of thousands of kilonewtons, slams into the thin interstellar medium, spawning shock fronts. These collisions act as immense cosmic accelerators, harnessing magnetic forces to propel protons and electrons to levels that demand enormous earthbound facilities to replicate. The American Association of Variable Star Observers rallies hobbyist input for nova research via uniform light measuring standards. Eyewitness spotters gauge luminosity against reference stars, whereas digital CCD imagers deliver exact magnitude data, uncovering fine fluctuations in the nova's brightness profile. Contributions from countless amateur stargazers around the world offer the detailed timing that pro facilities, juggling numerous objectives, can't sustain for single events. V1935. Centuries' luminosity progression adheres to templates refined over years of nova examinations. The surge from obscurity to visible to the naked eye levels usually spans days to weeks. The maximum glow might persist for days up to months, influenced by the white dwarf's heft, the pace of material intake from its partner, and the makeup of the hurled-out ejecta. The fading stage nova outbursts can persist for months or even years, occasionally featuring secondary surges when various physical mechanisms take control of the star's luminosity. Spectroscopic analysis uncovers the nova's elemental signatures. Initial observations often display wide emission lines from hydrogen, helium, and more massive elements traveling at rapid speeds, indicating the outflowing shell's expansion. As the nova progresses, these spectral features become narrower and relocate as the expelled gases cool and slow down. In time, forbidden emission lines emerge, which are possible only in the ultra-low density conditions of expanding nova envelopes where atomic collisions are rare, occurring perhaps once every few hours or days. The distances to V1935 Centauri and V79 and 94 Sagittarii are still imprecise, though they likely surpass a few thousand light-years. Consequently, the blasts we detected in September 2025 truly happened thousands of years earlier, during the early stages of human society's shift toward farming and fixed communities. The radiation from these cosmic detonations has journeyed across the void of space for a duration exceeding our documented past, reaching our planet right in the midst of this extraordinary period. Hobbyists equipped with basic tools can make valuable contributions to nova monitoring. A DSLR camera, paired with a long focus lens, is sufficient to capture images of both events at their peak visibility. Those relying on eyesight, aided by binoculars or compact scopes, can gauge brightness levels by matching the novae against reference stars with established magnitudes. Advanced enthusiasts using CCD imagers and photometric filters supply detailed measurements that enhance data from experts. The convention for assigning nova labels draws from long-standing astronomical customs and cataloging protocols. V1935. Centauri earned its enduring variable star label as the 1935th entry in the Centaurus asterism. The V denotes a variable object, one whose light output fluctuates periodically. Such fixed identifiers supplant provisional monikers which could incorporate the finder's family name, the detection date, or identifiers from diverse sky surveys. The development of dust stands out as a captivating phase in nova development. From weeks to months post-detonation, certain novae undergo sharp fades as fresh dust particles form within the chilling outflow. These obscuration episodes might drop the object's apparent magnitude by multiple steps, with tiny grains intercepting and redirecting the escaping photons. Ultimately, the dust cloud either evaporates or gets vaporized by ongoing stellar emissions, unveiling the core white dwarf once more. The power unleashed in nova blasts vastly overshadows anything in our earthly realm, yet pales beside supernova in scale. An average nova unleashes roughly the same energy as the Sun produces across about 10,000 years, sufficient to sustain global human energy demands for billions of years under today's usage patterns. Still, this amounts to just a minuscule portion of the colossal output from supernovae, which can rival the glow of whole galaxies for weeks or months. Repeated novae disrupt the notion of isolated blasts. Certain white dwarf setups trigger recurrent outbursts on fairly regular intervals, sometimes as often as every few decades in the quickest cycles. Over cosmic timescales, these setups might endure scores of such events, slowly building up accreted matter until nearing the Chandrasekhar threshold, at which point the dwarf could detonate as a Type 1 supernova. Expert monitoring of the September novae persists across a broad spectrum of wavelengths. Earthbound instruments track shifts in visible light and spectral transformations. Orbital facilities like the Hubble Space Telescope could yield sharp views of the growing shells. Additionally, radio arrays might pick up synchrotron signals from high-speed particles within the ejecta. Classifying V 1935, Centauri V79, 94. Sagittarius as a classical nova, as opposed to various other kinds of stellar outbursts, depends on data from spectroscopy and the way its brightness changes over time. Dwarf novae, which arise from disruptions in accretion disks instead of thermonuclear blasts, usually exhibit distinct spectral features and less dramatic increases in luminosity. Luminous red novae, potentially resulting from the collision of stars, show varied hues and longer timelines in their development. Might any of these novae indicate phenomena more unusual than typical thermonuclear detonations? Existing observations back the view of them as classical novae. Yet the field of astronomy wisely questions early assessments. With additional information gathered from observations spanning multiple wavelengths, the underlying mechanics could uncover nuances that sharpen our grasp of these specific eruptions. The gamma-ray signal, detected from V 1935 Centauri, positions it within a growing group of gamma-ray novae that question established theories of nova behavior. Such intense energy outputs imply that particle acceleration happens far more effectively than experts once believed feasible in nova settings. The underlying processes might include reconnection in magnetic fields, acceleration via shocks, or additional pathways that connect nova blasts to more powerful events such as remnants of supernovae. While monitoring these cosmic blasts throughout the electromagnetic spectrum, the firm ground of Earth was gearing up to show that the dynamics deep within our world rival those of far-off stars. Part 7. Dissecting a cluster of quakes. Under Lake Maracaibo and the adjacent Zulia region in Venezuela sits one of the most intricate tectonic zones in South America. The Caribbean plate rubs against the South American plate at a border area featuring several fault networks, including the Bocono fault system, which stretches northeast-southwest across the Venezuelan Andes, the Oca Ancon fault, which runs east-west near the Caribbean shoreline, and the Santa Marta fault, which reaches into Colombia. For many years, these tectonic lines have built up tension, hoarding energy that inevitably bursts forth in abrupt shifts. The 6.2 magnitude quake at 2221 UTC on September 24th initiated as a break along a segment of one of these faults, about 8 kilometers below ground level. Given this modest depth, the seismic vibrations faced fewer chances to disperse and lose strength on their path upward, thereby heightening shaking over a wide area. The starting break likely spanned a few kilometers along the fault surface, with abrupt shifts of several meters that unloaded accumulated pressure from years or even decades prior. From the break area, seismic vibrations spread out at about 6 kilometers via the nearby bedrock. The first to reach monitoring stations in the area were primary waves, which are squeezing motions that produce to and fro shaking in line with their path. Next came secondary waves, generating the lateral shaking that usually inflicts the greatest harm on buildings. Slower-moving surface waves, though, often pack the heaviest punch in terms of devastation, causing the undulating sensations that observers reported enduring for minutes at certain spots. Merely 5.5 hours afterward, at 3:51 UTC on September 25th, another significant break hit nearly the identical zone. This 6.3 magnitude event started at a depth of 14 kilometers, somewhat deeper than the initial one, yet near enough to the surface to produce strong tremors. The follow-up quake probably took place on a neighboring fault section, set off by alterations in stress from the earlier break. The concept of stress redistribution accounts for the tendency of quakes to happen in groups. A rapid slide on one part of a fault alters the pressure distribution on adjacent sections. Certain spots face heightened pressure, raising the odds that they will snap soon. In the coming years, certain zones undergo a reduction in stress, making them briefly less prone to seismic activity. The break on September 24th evidently transferred strain to the adjacent fault section, which gave way just 5 hours afterward. At first glance, the gap between the 6.2 and 6.3 quakes appears minor, yet the logarithmic basis of the scale indicates that the latter unleashed roughly double the power of the initial one. Together, these paired fractures unleashed force comparable to one quake of magnitude 6.4 to 6.5, marking it as one of the most potent worldwide tremors in late September 2025. Various global seismic bodies announced varying intensities for the incidents, highlighting the intricacies involved in gauging such events. The United States Geological Survey relies on moment magnitude, derived from the overall energy output in the fault break. Meanwhile, the European Mediterranean Seismological Center might employ alternative measures, drawing from surface wave strengths or internal wave properties. Such variations in approaches, along with refinements from incoming data from more instruments, account for news outlets citing intensities from 6.1 to 6.3 for the opening quake. The series of aftershocks adhered to long-standing trends observed by experts over many years. The 5.8 magnitude tremor that hit later on September 25th exemplifies a common substantial aftershock less intense than the primary one, yet potent enough to inflict further harm and alarm. Omori's law, developed in the early 1900s, outlines the gradual decline in aftershock rates after big quakes. The biggest follow-ups usually happen in the days right after the main event, while lesser ones persist for weeks, months, or longer. The effects on people stretched into both Venezuela and Colombia. Their fairly shallow origins intensified ground motion, prompting alerts to clear tall structures in key urban areas. Online platforms buzzed with footage of swaying lamps, shaking panes, and crowds fleeing structures as crisis measures kicked in throughout the zone. Though early assessments of destruction stayed modest considering the quake's sizes, evaluation crews devoted several days to recording obvious harm to frameworks, alongside risks of enduring frailty in constructions and utilities. The local terrain sheds light on the reasons this spot yields such forceful shakes. The Maracaibo Basin arose from intricate clashes of the Caribbean and South American plates, forming an array of fault lines that handle persistent plate shifts. Lake Maracaibo lies inside a graben, a sunken segment flanked by normal faults undergoing continued strain. The oil reserves that lend economic value to the area originated in sediment-filled depressions shaped by identical plate dynamics responsible for the quakes. Gauging depths involves considerable doubt, particularly in intricate geological settings. The 7-8 kilometer figure for the initial quake and 14 kilometers for the follow-up stand as optimal approximations drawn from wave arrival data across numerous observation points. These levels situate both incidents in the shallow crust, where snapping under stress prevails over the bending deformation seen deeper down amid rising heat and force. The close timing of the quakes sparked inquiries into possible catalysts. Might sunspots, air pressure shifts, or external influences sway seismic timing? Prevailing expert agreement, backed by the United States Geological Survey and global seismic bodies, holds that no solid link ties space weather to quake patterns. Years of data crunching have yet to uncover dependable ties between solar bursts and tectonic unrest. Coronal mass ejections, geomagnetic disturbances, and seismic occurrences show no direct links. Yet, certain studies have examined subtler possible ties. Variations in air pressure might slightly modify the strain on fault lines, though these shifts are usually much smaller than those induced by tidal forces from the moon and sun's gravity. Such effects can be picked up by precise tools, but they are vastly outweighed by the levels of stress required to set off quakes on faults not already on the brink of breaking. The worldwide centroid moment tensor catalog offers in-depth breakdowns of fault alignments, sliding motions, and break patterns for the Venezuelan quakes. These spherical plots indicate the actual fault surfaces that shifted and their movement vectors, data that aids experts in grasping local stress patterns and forecasting segments at higher future hazard. Right now, statistical methods in seismology provide the sole dependable way to anticipate earthquakes. After big tremors like Venezuela's, the odds of further significant shakes in the area rise briefly because of aftershocks and stress redistribution. Still, this heightened chance endures for just weeks or months and won't pinpoint precise timing or spots for follow-up events. In quake-prone areas such as Zulia State, construction regulations and readiness plans undergo constant evaluation. The limited destruction from the 6.2 and 6. 3 magnitude events probably stems from lucky circumstances and recent advances in building practices. Current quake-resistant standards demand that edifices endure intense ground motion, even if aging structures could still suffer harm or topple. Might stronger quakes strike the region soon? The underlying geology definitely permits more intense ones. Fault networks near Lake Maracaibo have sparked magnitude 7 events in the past, and the area's plate dynamics imply these will keep happening sporadically across eons. That said, experts can't say if the subsequent big slip will come in days, years, or decades. This series of Venezuelan tremors illustrates how Earth's rigid layers unleash spectacular bursts of power on timescales humans can witness, all governed by principles that span geological eras. Strain builds gradually as plates scrape by one another at speeds of centimeters annually. Once the buildup surpasses the rock's endurance, abrupt snaps discharge ages of pent-up force in mere moments of fierce jolting. With aftershocks still jarring the boundary between the Caribbean and South American plates, focus shifted to the cosmic realm, where a different kind of outburst was emerging on a scale that overshadows earthly shakes. Part 8. The Sun at its height. Solar Cycle 25 hit its zenith in 2024 and 2025, turning our usually calm star into an agitated behemoth able to fling massive plasma blobs weighing billions of tons through the solar system. On September 24th and 25th, stellar blasts illuminated southern hemispheres while tremors rocked Venezuelan ground. Metrics of solar vigor depicted a star in near-full rage. The 10 to 7 cm radio emission, a vital gauge of solar dynamism, lingered between 180 and 190 solar flux units in late September. This daily reading from radio observatories ties closely to the count and strength of turbulent zones on the Sun's face. Levels over 150 signal-boosted solar output, whereas those exceeding 200 point to highly dynamic states that can spawn significant space weather phenomena. Sunspots narrate the tale of magnetic turmoil brewing in the Sun's outer layer. These shadowy spots, frequently sunspots, which dwarf Earth in size, emerge in regions where intense magnetic field lines burst through the Sun's surface, inhibiting the typical convective flow of heat. Within the cores of these sunspots, the magnetic field intensity can surpass 3,000 Gauss, about 6,000 times more potent than Earth's surface magnetism. Greater numbers of sunspots typically signal increased chances for magnetic field lines to twist, link up anew, and unleash pent-up energy through solar flares and coronal mass ejections. Yet, mere counts of sunspots offer just a glimpse into the intricate dynamics of solar maximum phases. At the height of activity, the Sun's magnetic field twists into a chaotic tangle, far from the straightforward dipole configuration that prevails in quieter solar minimum periods. Active regions clusters of sunspots linked by arched magnetic loops can endure for weeks or even months as they spin across the solar disk and sporadically trigger dazzling outbursts observable by probes across the inner solar system. Among the most striking features of solar maximum phenomena are coronal mass ejections. These incidents kick off when magnetic field lines in the Sun's outer atmosphere grow overly contorted and strained, abruptly breaking and reforming to transform stored magnetic power into the motion of charged particles. This mechanism hurls massive plasma clouds, weighing billions of tons, outward into space at velocities from 250 kilometers in slower instances to more than 3,000 kilometers in the swiftest blasts. At NOAA's Space Weather Forecasting Hub, experts monitor these solar tempests via the WSA-NL model, an advanced computational tool that simulates the journey of CMEs across the heliosphere. This system partitions the cosmos into a 3D lattice stretching from the Sun past Earth's path, forecasting shifts in solar wind velocity, particle density, and magnetic alignment as these plasma blobs navigate the solar system. Although Enlil shines in estimating broad arrival windows and strengths, it falls short of detailing every nuance in a CME's form and dynamics. The fall equinox timeframe often heightens space weather consequences via the Russell-McFerrin effect. This alignment stems from how Earth's magnetic field aligns with the interplanetary magnetic field borne by the solar wind. In equinox seasons, the setup promotes reconnection between the solar wind's fields, Earth's magnetosphere, and incoming particles, frequently sparking fierce geomagnetic disturbances from even mild solar events. Space weather consequences reach well past the mesmerizing auroral lights that draw widespread fascination. Geomagnetic upheavals can interfere with high-frequency radio signals vital to air and sea transport, compel satellite teams to tweak orbits amid heightened drag from the atmosphere, and in severe scenarios, endanger electrical grids via currents induced in the ground. NOAA employs rating systems like the G scale for geomagnetic storms, the S scale for solar radiation events, and the R scale for radio disruptions to aid sectors in anticipating and handling space weather threats. Encounters between coronal mass ejections and comets serve as ideal testing grounds for plasma physics in scenarios unfeasible to mimic on our planet. Ion tails develop as solar wind yanks electrons from neutral gases in a comet's surrounding haze, generating ions that stream along magnetic field lines directly sunward. Such tails may stretch for millions of kilometers across the void, offering tangible signs of the unseen magnetic interactions linking our star to lesser objects in the solar system. Upon colliding with a comet, a CME can spark vivid and eye-catching interactions. The European Space Agency's stereo probes captured one in 2007, where a coronal mass ejection sliced off Comet Encke's ion tail via magnetic reconnection. The severed tail floated apart from the comet across hours as a fresh tail formed from pristine materials that highlight the ever-changing dynamics of space weather phenomena. The solar maximum in 2025 offered a vibrant setting for 3I Atlas as it ventured toward the inner solar system. In contrast to earlier interstellar objects that crossed paths with our Sun amid calmer phases of the solar cycle, this visitor faced space weather influences at their height of strength. The heightened rate of coronal mass ejections, CMEs, combined with the object's path across the ecliptic plane, the region where solar system events mostly cluster, increased the chances of notable encounters. The mechanics of CME spread encompass intricate magnetohydrodynamics spanning from the movements of single particles to formations bigger than planetary paths. Swift CMEs may catch up to slower solar wind streams, forming compressed zones and shock waves that boost particles to elevated energies. When several CMEs collide, they can fuse into bigger, more intense disruptions or generate elaborate magnetic setups that amplify particle speeding and magnetic reconnection processes. Experts in space weather forecasting keep tabs on diverse data streams to follow solar events and anticipate effects on Earth. The Solar Dynamics Observatory delivers non-stop, detailed visuals of the Sun's surface and corona across various extreme ultraviolet wavelengths. The Solar and Heliospheric Observatory keeps an eye out for CMEs bursting from the Sun's hidden side. Positioned between Earth and the Sun, the Advanced Composition Explorer offers early alerts on approaching solar wind disruptions. Hobbyists in amateur radio form a casual worldwide system for observing space weather impacts on our planet. During geomagnetic disturbances, high-frequency radio signals shift markedly, at times boosting far-reaching transmissions via stronger ionospheric bounces, yet at others weakening them through greater absorption and diffusion. Such on-the-spot accounts supplement official data from dedicated monitoring sites. This ongoing solar maximum seems to exhibit a dual peak structure observed in certain past cycles, starting with a surge in 2024 and sustaining strong levels into 2025. Such a prolonged peak period suggests that heightened space weather hazards could linger beyond the usual 11-year rhythm, keeping circumstances ripe for striking solar terrestrial events through 2026. Capturing auroras through photos and sightings has surged in appeal amid the present solar maximum, with platforms buzzing from stunning shots of emerald, crimson, and violet glows swirling over polar and near-polar regions. These spectacles arise when charged bits from solar eruptions collide with Earth's upper air layers, rousing oxygen and nitrogen molecules that release signature hues upon settling back to their base states. The solar wind transports ingrained magnetic structures born in the sun's corona, extending throughout the solar system as the plasma expands. These interplanetary field lines link worlds, comets, and probes in an expansive grid of electromagnetic sway, reaching out to the heliopause. The edge where solar wind force equals interstellar medium force, about 100 times more distant from the sun than Earth. While monitoring solar storms advancing across the inner heliosphere in late September 2025, a specific focus drew the interest of space weather specialists and stargazing fans, an interstellar traveler navigating this stellar tempest en route to its initial brush with another planet. Part 9. 3I Atlas on approach. In the pre-dawn moments of July 1st, 2025, the Asteroid Terrestrial Impact Last Alert System telescope array spotted an unusual sight drifting amid the starry backdrop. Early scans pointed to a dim, comet-resembling body, but swift orbital computations soon exposed its authentic character. 3I Atlas stands as merely the third verified interstellar guest in humankind's records, succeeding the enigmatic Oumuamua in 2017 and Comet Borisov in 2019. This label encapsulates both its detection and importance. The 3I beginning signifies the third such extraterrestrial body recorded by the International Astronomical Union, whereas Atlas honors the telescope array that initially detected this stellar drifter. In contrast to earlier arrivals, 3I Atlas entered a prime viewing period, sufficiently luminous for in-depth analysis, tracing a path close to the ecliptic where solar system motions mostly cluster, and nearing us amid peak solar activity that presents rare chances to examine our sun's effects on incoming cosmic debris. The intruder's path details underscore its extraterrestrial roots. Its route forms a hyperbola with eccentricity well above unity, showing it carries ample velocity to break free from solar gravity. With an orbital tilt near 175 degrees, 3I Atlas travels retrograde against the planetary norm, opposing the usual orbital currents in our system. Contemporary simulations estimate its dimensions from a few hundred meters to perhaps 15 kilometers in diameter. Despite considerable doubt in these figures, even top-tier earthbound scopes can't capture clear pictures. To observers, it resembles just a hazy stellar speck encircled by a subtle envelope of vapor and particles. Determining its scale relies on guesses regarding albedo, makeup, and outgassing factors, all mysterious for something born near another sun. On October 3, 2025, a landmark event unfolds in the study of interstellar intruders. 3I Atlas will skim within 0.19 AU of Mars, about 28 to 30 million kilometers from the Crimson World. Such proximity enables exceptional scrutiny via Martian satellites, such as ESA's ExoMars Trace Gas Orbiter, NASA's Mars Reconnaissance Orbiter, and additional probes offering a stellar vantage for probing the newcomer. Harvard's Avi Loeb likened this Martian rendezvous to a surprise meeting between a cosmic outsider and our adjacent planet. The Mars Reconnaissance Orbiter's advanced imager, which discerns Martian terrain down to 30 centimeters, ought to yield pixel resolutions around 30 kLON when aimed at 3I Atlas at periapsis. Though this won't uncover the core's topography, it could differentiate a dense heart from a spread-out gaseous halo. These sightings hold value far beyond basic visuals. During the Mars pass, spectral scans might uncover the makeup of vapors venting from the intruder's heart, as sunlight releases primordial ices. Anticipated signatures feature CN, cyanogen, CO, carbon monoxide, and CO2, carbon dioxide, substances offering solid proof of its chemistry and insights into its home star's environment. Hobbyists across the globe have supplied vital data on 3I Atlas during its inbound journey. Initial accounts pointed to quicker than anticipated flaring as it drew nearer the sun. While such raw brightness profiles need precise adjustments and validation, its location in southern skies benefits southern watchers, yet those in the north can follow it in pre-dawn skies as it clears their southern skyline. Leading facilities keep organizing viewing efforts via groups such as the American Association of Variable Star Observers and the Minor Planet Center coordinates these initiatives to examine fluctuations in luminosity, alterations in tail structure, and shifts in spectral properties. As 3I Atlas encounters heightened solar radiation on its approach leg, its path across the inner solar system presents numerous chances for monitoring that persist into the beginning of 2026. After passing by Mars on October 3rd, 3I Atlas heads onward to perihelion, reaching its nearest point to the Sun on October 29th at around 1:36 to 1:4 AU. At this range, it stays beyond Earth's orbital path, yet remains accessible to terrestrial telescopes and orbital instruments. On December 19th, 3IA Atlas achieves its minimal distance from Earth, about 1.8 AU, or roughly 270 million kilometers. To put that in perspective, it's nearer than Mars ever gets at opposition, offering prime visibility for expert facilities and hobbyist stargazers using basic equipment from late 2025 through early 2026. How the visitor acts close to perihelion might indicate if it adheres to standard comet development or shows distinctive traits tied to its extrasolar background. Solar warmth could release icy materials locked away for eons while traversing the void between stars. Such venting might trigger sharp rises in brilliance, tail formation, or additional effects that set interstellar objects apart from native comets. The shape of the tail stands out as a particularly captivating element in 3 Atlas studies. Expert photos reveal ion streams pointing away from the sun, aligning with standard cometary activity, whereas certain backyard watchers describe dust features oriented ahead, seemingly defying conventional comet dynamics. These seeming inconsistencies probably arise from the distinct mechanisms behind dust and ion tail creation, not from unusual processes. Dust tails arise from radiation pressure, the subtle yet steady push of sunlight on tiny grains released from the core. These grains trace arched paths under the influence of both solar radiation push and gravity's pull, forming the elegant bends seen in typical comet images. Depending on the angle of view and the watcher's stance relative to the orbital plane, dust tails might seem directed in diverse ways. Ion tails, by contrast, emerge from a wholly separate set of principles. The solar wind ionizes gases in the surrounding haze by removing electrons, yielding ions that link magnetically to the wind's embedded field lines. These ions stream directly outward from the sun following those field lines, producing slender linear tails that shift as the solar wind's magnetic alignment fluctuates. Uncertainties about the dimensions and makeup of 3 Atlas highlight the core difficulties in probing bodies across vast interplanetary gaps. No telescope, however advanced, can discern surface features on items tinier than large asteroids when they're more than a few AU distant. Guesses at size rely on luminosity data, presumptions regarding albedo, and simulations of light reflection back to our planet. Certain news outlets have suggested 3 Atlas might span up to 15 meters, though such figures warrant skepticism pending confirmation via thermal physical analysis, integrating visible light readings with IR detections of heat output. The degree of outgassing, the volume of vapor and particles ejected per unit size, further affects perceived brightness, adding layers of complexity to sizing efforts. The inbound path of the visitor aligns with a stunning astronomical occurrence, ensuring October 2025 becomes an unforgettable period for those who gaze at the heavens. Worldwide, it's essential to grasp what occurs when coronal mass ejections from our sun interact with ancient wanderers drifting through interstellar space. Part A is on the way. Although 3 Atlas grabs attention as an interstellar guest, October 2025 sets the stage for another stunning astronomical display that might outshine it. The comet C2E25 R2, spotted in SOHO's SWAN data by hobbyist astronomer Vladimir Bezugi on September 11th and 12th, is hurtling toward its nearest pass by Earth on October 20th and 21, possibly becoming visible to the unaided eye right around the time 3I Atlas swings past Mars. The tale of its discovery highlights the impact of citizen science in today's astronomy. SOHO, the Solar and Heliospheric Observatory, keeps a constant watch on the Sun's corona and the nearby space around it. The SWAN instrument, designed to chart hydrogen glows across the heliosphere, sometimes picks up comets as they flare up and start releasing gases while heading into the inner solar system. While poring over open-access SWAN images, Vladimir Bezugi detected a glowing body that didn't align with any cataloged comet or asteroid. His thorough review of various frames verified its cometary traits and yielded initial orbit estimates, indicating a long-period comet on its debut recorded trip toward the inner solar system in recorded history. Comet SWAN hit perihelion, its closest point to the Sun, on September 12, 2025, mere days following its detection. That schedule accounts for the swift surge in brilliance that first drew Bezugli's eye. Comets usually shine brightest near perihelion, as intensifying sunlight vaporizes frozen materials from their cores, forming the signature fuzzy coma and tail that render them observable from our planet. The path of its orbit supports strong sightings in October from either hemisphere, with southern viewers getting the edge at the start. As the month advances, the comet's alignment with Earth and the Sun shifts favorably for those in the north, creating prime chances for countless backyard stargazers and everyday enthusiasts. Forecasts for its glow point to a magnitude between 4 and 6 at peak proximity to Earth, bright enough to spot without aids in clear, dark skies, although binoculars or modest scopes would uncover richer views of its hazy envelope and streaming tail. Such projections come with notable caveats, since comets' performances are famously erratic, particularly for fresh ones venturing inward for the first time on record. This alignment crafts an ideal overlap of sky spectacles in late October 2025. The new moon around October 20 and 21 clears away moonlight that can obscure dim sky features. The yearly Orionid meteor shower hits its zenith on those very evenings, thanks to particles from Comet Halley crossing our planet's path. Observers might catch sight of a vivid comet, dozens of shooting stars hourly, and the ongoing path of 3I Atlas, all in the same ideal stargazing windows. As a long-period resident of our solar system, Comet SWAN stands in stark contrast to 3I Atlas's origins from beyond. Even so, both probably harbor comparable frozen substances, water ice, carbon monoxide, carbon dioxide, and assorted organics. But they originated in vastly distinct settings. Comet SWAN coalesced from remnants in the far-flung zones of our own solar system about 4 billion years back, likely lingering in the remote Oort cloud until some gravitational nudge propelled it inward. Consequently, the research puzzles each raises vary greatly. 3I Atlas sheds light on other star systems, formation mechanisms, the chemistry occurring in interstellar space, and the influence of cosmic rays on substances over multi-million-year voyages across the cosmos. Comet SWAN offers insights into the environment of the primordial solar system, the makeup of the Oort cloud, along with the effects of solar warmth on untouched cometary substances during their initial near-Sun passage. Plenty of imaging chances exist for expert and hobbyist stargazers amid October's dual comet show. Broad-angle lenses allow snapping both bodies within a single shot, recording their positions relative to each other, luminosity levels, and tail formations for side-by-side analysis. Sequential imaging might uncover shifts in the coma shape, tail direction, and total glow. With fluctuating solar wind patterns and the body's ever-changing separations from our planet and the Sun each day, the erratic progression of comet luminosity brings thrill and unpredictability to the month's observation window. Certain comets far surpass forecasts in brilliance, sprouting dazzling tails and hitting brightness levels that render them obvious to the unaided eye, even amid city glow. Others fall short, refusing to intensify as anticipated, or breaking apart from intense solar warmth, which curbs their spectacle. Comet Swan's brief record of sightings complicates accurate forecasts. In contrast to recurring comets that cycle back predictably, enabling scientists to track their tendencies across several visits, fresh, long-orbit comets such as Swan lack any prior record for their luminosity patterns, rates of gas release, or resilience against solar heat. The chance for striking tail growth enhances the allure of October's comet sightings. Both particle and plasma tails may stand out markedly as solar wind ramps up amid peak solar cycle activity. Tail severance incidents, in which solar eruptions detach plasma tails from the comet cores, could appear live via scope views, granting uncommon views of cosmic weather dynamics at work. Hobbyists monitoring comets use diverse approaches to follow luminosity shifts and form alterations. Eye-based brightness assessments match the comet's glow against stars of established magnitudes, yielding info that pro-facilities can't gather non-stop. Imaging via digital setups and CCD gear delivers sharper data while capturing evolutions in the coma and tail elements. Curiosity surrounds whether Earth could cross paths with fragments from Comet Swan, heightening interest in October's watch. Should our world's path overlap the comet's dust path from earlier inter-system transits, a subtle meteor display might occur as bits burn up in our atmosphere. Yet for recently spotted comets lacking defined debris paths, such occurrences stay quite speculative. Spectral analysis of the pair in October might expose compositional parallels and contrasts that shed light on their origins. Advanced facilities with spectrometers can spot glow from particular molecules like CN, C2O, and NH2, signaling which ices are vaporizing from the cores due to sun's heat. Such molecular signatures offer straightforward clues to makeup and birth settings. Practicalities for catching October's twin comet event suit those with unlit skies and open vistas. City lights harshly dim subtle sky sites, so countryside or remote spots prove vital for prime viewing. Late October weather differs widely by region, demanding adaptable schedules for effective sessions. Binoculars frequently outperform. Binoculars are ideal for amateur stargazers. Their broad perspective captures the entire comet, including its core, surrounding haze and streaming tail, within the full scene, avoiding the narrow focus that might obscure the bigger picture. Thieves 50 or Teniac 50 models stand out as top picks, offering sufficient light collection to uncover subtle features without sacrificing easy observation postures. The rare alignment of two luminous comets in October 2025 presents exceptional chances for side-by-side analysis. Such parallel sightings might highlight variations in the haze's hue, the tail's direction, and the comet's general shape, which stem from their distinct backgrounds and developmental paths. Capturing sequences of photos over multiple evenings could track how each celestial body reacts to shifting solar winds and observational perspectives. Around the globe, expert facilities have planned joint monitoring efforts for these visitors, guaranteeing thorough data from various parts of the light spectrum. The Hubble Space Telescope could capture sharp pictures revealing fine structures beyond the reach of Earth-bound setups. Meanwhile, radio arrays might pick up signals from molecules that disclose the makeup and heat profiles in the growing hazy zones. When it comes to watching comets, risks are far lower than those for solar or lunar eclipses. These icy wanderers present no immediate dangers to viewers and demand nothing more than standard safeguards for evening outdoor pursuits, no filters or gear required. Key hurdles include scouting clear sky locations, coping with atmospheric variability, and keeping gear operational amid chilly late autumn evenings. The arrival of two dazzling comets under prime skies in the same season boosts learning prospects immensely. Classrooms, stargazing groups, and community observatories frequently host dedicated sessions to draw in beginners to the field of comet studies, while allowing veterans to contrast bodies with vastly different provenances. Such gatherings promote awareness of science and honor the awe of universe events accessible to all who venture out and gaze skyward. With October 2025 drawing near, preparations are underway for a period brimming with extraordinary sky happenings. An extrasolar guest passing near Mars, a long-orbit comet hitting maximum glow, lively sunspot activity, and ongoing tremors from quakes in Venezuela. This overlap of occurrences from ground-shaking geology to deep space wonders forms a sequence that questions easy notions of random alignments in the cosmos. Yet, prior to delving into the profound implications of this striking bunching of occurrences, it's essential to review the tendencies our brains naturally spot when striking events bunch up across time and location. Part 11. Are these cosmic flukes or meaningful designs? We'll build a schedule outlining the striking overlap of happenings in late September and early October 2025. On September 23rd, V1935 Century bursts into unaided eye view in Curacao. September 24th brings a 6.2 magnitude quake hitting Venezuela at 20:22:21 UTC. The next day, September 25th, 7994, Sagittarius detonates in Sagittarius, followed by another 6.3 magnitude tremor cracking the same Venezuelan area. Just 5.5 hours after the initial one, a 5.8 magnitude aftershock strikes. In late September, ENL forecasts indicate solar plasma bursts intersecting the 3I Atlas path. October 3rd marks the interstellar object's closest pass by Mars at 0.19 astronomical units. From October 20th to 21st, Comet Swan nears Earth most closely, aligning with the new moon and the height of the Orionid meteor display. On October 29th, 3I Atlas achieves its nearest solar point at 1.36 astronomical units from the Sun. This tight packing of intense episodes spanning stars, Earth movements, sun dynamics, and interstellar visitor dynamics crafts a storyline that seems almost preordained. A pair of stars bursts forth in mere days. Two significant quakes tear through the Earth just hours apart. Solar flares weave across the cosmos in the very same week. An object from beyond our system nears Mars as a local comet hits its brightest phase. This grouping goes beyond mere chance, edging toward a kind of universal harmony. Our minds develop to spot significant designs amid chaotic surroundings, a mental tool that aided early humans in spotting faint links between surroundings and risks or prospects. This instinct for patterns runs on autopilot, frequently under the radar of awareness, hunting for ties that suggest cause and effect, even if it's just association at play. Apophenia, that drive to find purpose in scattered data, stands as both a boon and a flaw in how we think. The very thought processes that helped forebears track seasonal shifts, forecast atmospheric changes, and grasp group interactions can also trick us into seeing import in random bunches of disconnected happenings. The established scientific community provides straightforward insights into the September-October alignment. The U.S. Geological Survey insists that no proven link ties space weather to seismic activity. Years of examining overlaps have not uncovered solid ways to forecast quakes from sun-related events. Expert earthquake specialists stress that foretelling tremors stays out of reach with today's techniques, no matter if they draw from ground signs or cosmic factors. In the same vein, star experts see novae as expected outcomes of paired star life cycles, where white dwarfs gather enough stuff from partners to spark explosive nuclear reactions. Nova blasts align with star mechanics, not pulled by Earth or solar influences. V1 1935, Centurin V79, and 94 Sagittarius serve as typical instances of routines playing out across the Milky Way routinely. Sun experts examine coronal mass ejections as standard results of magnetic shifts in the Sun's outer layer amid high solar cycles. Such incidents ramp up during top activity phases, positioning late 2025 as a probable window for several CME outbursts. The clash of solar bursts with comet substances follows familiar rules of charged particle behavior, not strange occurrences. Still, accepting these expert views doesn't mean downplaying the striking quality of this time-based grouping. At times, the cosmos lines up in manners that push luck toward the poetic, even if the real drivers stay ordinary. The challenge arises: how do we make room for sharp doubt alongside fitting awe? Embracing both lets us value the odds of this bunching while honoring evidential limits. We might note that dual novae hitting visible brightness in days marks a rare event without tying it to ground shakes. We could see magnitude 6 quakes hitting hours apart in one area as fitting stress shifts and follow-up tremors, sans any sun weather pull. We might admire the approach of 3 atlases amid peak solar times, knowing it stems from good viewing setups rather than otherworldly timing. We could rejoice in the overlap of 2 vivid comets under prime sight conditions without claiming stellar powers staged it for our sake. Media timing. It heightens the overwhelming sense of everything happening simultaneously via focused news coverage and the boost from social platforms. When several intense incidents unfold over just a few days, media loops and digital conversations build feedback loops that solidify views of their importance. The mental effects of such overlapping reports can turn random groupings that are truly chance-based into something that seems profoundly significant beyond what data crunching would justify. Findings from archaeology and history show that people have long looked for grand universal meanings in earthly happenings. Early societies saw comets as harbingers of doom, solar eclipses as signs of godly anger, and alignments of quakes with comets as messages from the beyond. Such ingrained habits linger today, even as factual insights blend with our innate drive to impose purpose on seemingly haphazard bunches of events. The key is to uphold analytical precision while recognizing the stirring and artistic allure of these striking overlaps. We might savor the elegance of heavenly alignments without ditching logical scrutiny. We can revel in awe at the cosmos's sporadic setups without leaping to notions of deliberate patterns or concealed links. Rival theories merit equal attention as long as we draw firm lines between verified facts and imaginative what-ifs. The view of these clusters as separate relies on robust natural principles. Astrophysics accounts for stellar blasts, geology for seismic shifts. Sun science covers solar flares and ejections, while celestial orbits handle comet paths. Every element adheres to proven rules of nature, functioning on its own. The idea of cosmic harmony steps into riskier ground, hinting at faint ties among events that conventional experts haven't spotted or grasped yet. This angle doesn't toss out the laws of physics. Instead, it argues that our grasp might have gaps that could someday uncover real links across disjointed fields. Both views can thrive side by side in the mind if we guard proper lines of knowing. Proven knowledge claims the spotlight due to its wealth of evidence and track record in forecasting. Untested ideas warrant probing, but only if they're kept apart from confirmed truths and spark-checkable forecasts. The fall equinox time adds backdrop that calls for no outlandish theories. The Russell-McFerrin effect sets up angles that intensify space weather effects in September and October, rendering this stretch more prone to notable magnetic storms by the numbers. Reports note seasonal trends in quakes in certain areas, although the causes are murky and influences usually mild. Traditional mythic structures lend vivid tales without demanding face value belief. For ages across societies, comets have stood for transformation, chaos, and signals from the stars. Quakes embody the planet's firm crust, exposing its restless side. Star bursts highlight the fierce splendor of universal growth. These symbolic ties furnish compelling plot pieces that echo profound mental templates, all while standing clear of actual physical drivers. The call goes out to audiences and perusers to juggle rival ideas with a loose grip, valuing both factual discipline and storytelling magic. We might delight in the serendipitous vibe of heavenly incidents bunching up without forsaking rational analysis. We can delve into potential bonds while honoring bedrock science. We can toast the extraordinary even as we accept the everyday odds. Maybe the truest path lies in welcoming the unknown, while science progresses by staying receptive to new findings. It relies on meticulous observations, the development of hypotheses, and thorough experimentation instead of rushing to conclusions about intricate events. The alignment in September and October offers abundant data for both empirical study and creative inquiry. As long as we clearly separate observed facts from proposed ideas and verified knowledge, As we explore these topics further, a specific theoretical link warrants close scrutiny: the enduring question of whether space weather could affect earthquakes on Earth via mechanisms that are still not well grasped. Part 12. Space weather and earthquakes. The notion that solar flares might impact the timing of quakes stands as one of the longest-standing and most disputed ideas in the field of Earth-space interactions. For many years, scientists have noted apparent statistical links between different space weather events and earthquake patterns. However, no broadly endorsed physical process accounts for how electromagnetic disruptions from 93 million miles distant could initiate abrupt breaks in the planet's outer layer. The most compelling recent theory originates from investigator Stephen Burns, suggesting that reductions in solar wind density after fast-moving surges might generate an electromagnetic void capable of gently modifying stress patterns in the crust. In this framework, when a thick, rapid solar wind abruptly shifts to the thin, sluggish ambient solar wind, the resulting fluctuation in electromagnetic force on Earth's magnetosphere might, in principle, transmit via intricate linkage processes to affect how stress builds on fault lines. The underlying physics entails several stages, each adding layers of doubt and weakening. Initially, shifts in solar wind density would reshape and adjust the pressure within Earth's magnetosphere, the protective magnetic envelope that guards against much of space weather's impact. Alterations in the magnetosphere's structure could then tweak the electric flows in the ionosphere, the planet's upper layer that's conductive to electricity. Variations in these currents could generate electromagnetic waves that extend into the crust, potentially affecting piezoelectric stress in the rock crystals there. Every link in this suggested sequence deals with tiny effects, such as magnetic field shifts in nanoteslas or stress alterations in microstrains, levels thousands of times below what's required to set off quakes on faults not already on the verge of slipping. While the potential linkage pathways are theoretically present, their scale seems too minor to sway seismic events in typical scenarios. What remains firmly supported in research is the vast array of claimed correlations alongside a notable lack of proven causation. Investigations spanning decades have highlighted statistical ties between solar flare bursts and quake frequencies, the strength of geomagnetic storms and groupings of seismic incidents, and assorted space weather metrics with local earthquake records. Such links often seem robust in initial analyses, yet they commonly don't hold up when checked across varied timelines, areas, or quake datasets. Publication bias muddies the research landscape considerably. Findings showing positive ties between space weather and earthquakes tend to get submitted, published, and referenced more than those yielding no connection. This fosters a false sense of agreement in the field for links that might not truly exist or could be much less pronounced than the available studies imply. Efforts to combine various studies through meta-analyses typically reveal that the strength of effects diminishes with larger datasets and stronger methods. The United States Geological Survey's official, the stance endorsed by the international seismological organizations, asserts that no solid link has been proven between space weather phenomena and the onset of earthquakes. This finding draws from thorough statistical evaluations of worldwide earthquake records juxtaposed with detailed space weather archives covering several solar cycles. Once appropriate statistical adjustments are made, accounting for multiple testing, time-based groupings, and selection biases, nearly all claimed associations fade away or prove statistically irrelevant. Nevertheless, certain scientists persist in investigating more nuanced possible ties that could manifest solely in particular scenarios. Fluctuations in atmospheric pressure linked to geomagnetic disturbances might, in theory, modify the strain on tectonic faults. Yet these shifts generally amount to under 1 millibar, which is much less than everyday weather-induced pressure changes that exhibit no evident tie to seismic events. Another suggested pathway involves electromagnetic induction. Intense geomagnetic storms have the potential to generate electrical flows in conductive substances, such as subterranean aquifers and mineral deposits. Such induced flows might, hypothetically, modify electrochemical reactions within fault areas, possibly impacting fluid pressure in pores or the integrity of rocks in manners that could sway the timing of quakes. Once more, while the conceptual frameworks are present, their scale seems too minor to notably disrupt the well-documented processes in seismology. Gravitational influences provide a more viable path for interactions between space and Earth, albeit not via electromagnetic routes. Tidal forces from the Moon and Sun clearly affect earthquake patterns, with research indicating modestly heightened seismic rates amid peak tidal strains. These gravitational impacts are thoroughly comprehended, quantifiable, and function via proven physical principles that directly modify stress along fault lines. Might comparable gravitational forces from additional celestial bodies affect seismic events? Configurations of planets, though favored in various fringe hypotheses, yield gravitational pulls vastly weaker than those from lunar tides. Even major planetary groupings create tidal stresses on our planet that pale in comparison to standard lunar-solar tidal fluctuations. The difficulty in validating links between space weather and earthquakes stems from distinguishing true physical bonds from mere data illusions. Seismic events adhere to intricate statistical behaviors, encompassing aftershock chains, regional groupings, and time-linked patterns that can readily forge false ties with any fluctuating external factor. Space weather metrics likewise display self-correlations, cycles, and bunching that might mimic connections to quakes purely by chance. Effective validation demands pre-planned investigations that outline predictions, temporal spans, locales, and analytical techniques prior to data review. Protocols for blind assessments, in which experts scrutinize earthquake datasets unaware of aligned space weather states, could prevent inadvertent biases in choosing and interpreting information. Although such stringent methods are uncommon in published work, they remain crucial for confirming authentic links. What evidence would qualify as persuasive for ties between space weather and earthquakes? Primarily, the suggested process must exhibit physical feasibility via lab trials or conceptual simulations, illustrating how electromagnetic or particle influences could substantially reshape stress distributions in crystalline rock. Additionally, observed statistical patterns should demonstrate forecasting accuracy surpassing random expectation when evaluated forward-looking on fresh datasets. Finally, any real association would such relationships should be viewed as conditional instead of applying universally, functioning solely within specific tectonic environments, stress conditions, or fault configurations. It seems physically unlikely that broad correlations would impact every earthquake-prone area in the same way, considering the enormous variations in regional geology, stress regimes, and fault behaviors among diverse seismic areas. The sequence of earthquakes in Venezuela took place amid heightened space weather conditions, offering yet another instance in the ongoing discussion about potential links. That said, isolated occurrences don't establish any underlying patterns. Venezuela lies within a dynamically active tectonic zone where events of magnitude 6 happen sporadically yet foreseeably, driven by interactions at plate edges and the buildup of local stresses. Should a real tie between space weather and earthquakes exist, it would probably be understated and context-dependent, not bold and all-encompassing. These influences could appear only in fault networks nearing the breaking point, where even minor extra stresses might hasten the onset of ruptures by hours, days, or weeks without sparking quakes that were bound to happen anyway. Seismologists generally agree that the timing of earthquakes hinges mainly on regional stress development, characteristics of fault zones, and random elements within intricate nonlinear dynamics. Factors from outside, be they space weather, air pressure variations, or else probably contribute little relative to the overriding tectonic pressures that build up across years and discharge abruptly in large events. The most rigorous scientific stance recognizes both conceptual opportunities and the constraints of available data. We can't completely dismiss faint electromagnetic or gravitational interactions between space weather and earthquakes, yet no solid proof shows these effects strong enough to noticeably alter seismic events. Going forward, studies ought to prioritize mechanism-based physical models to pinpoint feasible pathways before hunting for patterns in raw observations, especially for effective earthquake readiness and hazard evaluation. Monitoring space weather yields no practical insights into seismic risks. Strategies for construction standards, crisis response, and community protection must continue relying on proven seismology, including details on fault networks, past seismic records, and estimates of probable hazards, not predictions from space weather. As we delve into these earthly ties, a far more conjectural issue emerges. Might bursts of energy from remote stellar blasts somehow shape Earth's weather patterns or Earth-shaping activities across extended periods? Part 13. Novae and Climate. The notion that stellar blasts could sway Earth's climate spans hugely disparate levels of power, separation, and duration compared to the space weather seismic idea we examined earlier. Although close supernovae might in theory alter our world's air layers and weather over eons, standard novae such as V1935, Centauri VV9994 Sagittari pack far less punch and lie vastly farther away, rendering any immediate ground-level effects essentially unattainable. To grasp the magnitudes at play, let's define them with unyielding accuracy. A standard nova unleashes power, matching the sun's full yield across about 10,000 years, roughly 10 to the 43rd joules. By everyday human measures, this appears colossal, enough to fuel global society for eons at today's usage levels. Still, this output radiates outward in all directions from the blast's origin, thinning out per the inverse square principle as it crosses the void between stars. 1935. Centauri probably resides thousands of light-years distant from our planet, so its outburst happened ages before societies arose, writing, farming, or lasting human communities. When this long-ago cosmic outburst finally makes its way to our solar system, the incoming energy has faded to something akin to the glow from a vivid star. Beautiful for stargazers to behold, but completely insignificant when it comes to influencing weather patterns or air composition. The radiation that eventually hits Earth from these September novae totals just a handful of additional light particles per square meter. That's even less extra energy than what a handheld torch would deliver from a short distance away. In terms of environmental impact, the combined output from both novae throughout their peak and fade-out periods wouldn't generate enough heat to noticeably warm even one mug of coffee. By comparison, closer supernovae stand out as real possibilities for cosmic effects on climate across deep geological eras. A supernova exploding within about 50 light-years of our planet could unleash sufficient intense radiation to profoundly shift atmospheric makeup. The gamma and X-ray bursts from such a blast might wipe out large swaths of the planet's ozone shield, letting more harmful ultraviolet light penetrate to the ground and possibly sparking widespread die-offs. Certain scientists have linked proximate supernovae to past mass extinctions in Earth's history, although the supporting data is still hotly contested and inconclusive. The Ordovician extinction event, which happened around 450 million years back, lines up loosely with signs of a nearby supernova. Yet, proving a clear cause and effect link over such immense timescales demands ironclad proof that simply isn't available right now. The ways supernovae could sway climate revolve around intricate chemical reactions in the atmosphere, not straightforward warming from heat. Energetic light particles from these starbursts can break apart nitrogen and oxygen in the upper air layers, forming nitrogen oxides that speed up ozone breakdown. With a thinner ozone barrier, greater amounts of sunlight's ultraviolet rays could hit the surface, harming habitats and reshaping worldwide weather through tangled cause and effect loops. Interactions with cosmic rays offer yet another route for stars to affect ground-level climate, albeit on vastly different magnitudes and durations than the September nova incidents. Certain hypotheses suggest that cosmic rays' supercharged particles, boosted by supernova blasts, could spur cloud development by acting as seeds for water vapor to condense around. Shifts in cosmic ray levels might, in theory, tweak cloud density and thereby influence planetary temperatures. However, lab tests backing this idea are scarce and fiercely disputed. The September novae could add a tiny bit to the overall cosmic ray pool across cosmic epochs, but any short-term effect on our planet's ray exposure would be impossible to spot. The cosmic ray bits propelled by V1935 Centauri and V794 Sagittarii would need millennia to cross the void between stars and arrive here, blending seamlessly into the steady hum of galactic radiation. News reports frequently mix up various kinds of star detonations and their earthly consequences, sowing mix-ups between real dangers and made-up perils. Stories claiming stellar blasts might disrupt climate often overlook the divide between close-up supernovae that could leave traces over eons and far-off novae that offer zero meaningful climate risk. Such blurring contributes to a wider trend of hype in astronomy, favoring thrilling tales over factual precision. The apparent link in timing between September's star flares and quakes on Earth gives ample opportunity for those inclined to spot patterns to weave imagined connections. While such stories capture the imagination, the immense energy differences render any immediate link physically impossible. The combined output from both novae, across their full visible durations, amounts to far less than a single second's worth of everyday solar illumination on Earth's surface. That said, investigating the interplay between star blasts and weather patterns continues to be a valid and captivating area of inquiry, as long as it emphasizes realistic processes unfolding on suitable timescales. Our galaxy witnesses about 1 to 3 such blasts every 100 years, so our world regularly faces intense radiation bursts from comparatively close stellar detonations throughout its multi-million-year geological past. Traces of cosmic ray impacts in rock layers occasionally reveal hints that align with supernova occurrences. Iron-60, an unstable isotope mainly forged in these stellar upheavals, shows up in ocean floor manganese iron deposits and polar ice samples, offering solid proof that our planet now and then endures heightened cosmic ray doses from extraterrestrial origins. These atomic markers provide intriguing insights into potential ways starbursts could affect Earth across vast epochs, though their effects span millions of years, not mere weeks or seasons. Findings of Iron-60 indicate that our world underwent a spike in cosmic ray influx around 2 to 3 million years back, likely tied to blasts in adjacent star groups. Whether these intensified rays truly shaped local weather systems, air makeup, or life's development is still a matter of debate and ongoing investigation. Certain hypotheses link shifts in cosmic ray intensity to glacial periods, yet the pathways are hypothetical, and supporting data falls short of certainty. Regarding the September 2025 novae, their potential weather effects are strictly theoretical and virtually non-existent. These remote star eruptions add nothing detectable to our planet's energy balance, modify no chemical reactions in the atmosphere, and sway no environmental factors. They serve as stunning illustrations of how stars develop and erupt, happening at vast cosmic removes where we can watch and analyze them harmlessly. The key takeaway is to keep a balanced view of celestial magnitudes and the gap between thrilling space happenings and tangible ground-level consequences. The cosmos constantly unleashes awe-inspiring spectacles like star detonations, galaxy smash-ups, and black hole unions that unleash colossal power, yet they stay too remote or fleeting to meaningfully touch our world's weather dynamics. Earth's climate mainly reacts to fluctuations in sunlight, shifts in air components, sea current flows, and eruptive geology. Local and inner solar system dynamics play out over spans from annual cycles to thousands of years. Though unusual space factors aren't entirely dismissible on deep-time geological levels, they pale beside the main drivers molding our planet's climatic history. The allure of tying far-off star bursts to local happenings stems from our innate drive to uncover purpose and order amid seeming chaos. Such mental habits helped early humans spot real ties in their surroundings, yet they can also trick us into seeing import and chance alignments of unrelated occurrences. Having delved into Earth-cosmos links, we now shift focus to the rogue object from beyond that could yield the clearest, most prompt chance to examine our solar realm's exchanges with materials from alien star realms. Part 14. Interstellar intruders as system explorers. 3 Atlas stands as much more than a mere oddity from interstellar space, holds what may be our most exquisite natural instrument, yet for examining the ways our sun engages with substances originating from other star systems. Although Oumuamua sped away too fast for in-depth analysis, and 2I Borisov stayed fairly remote during its journey, this latest interstellar guest presents remarkable chances to scrutinize the impacts of solar weather on material that has drifted for eons across the voids between stars. The very alignment of 3I Atlas sets it apart in heliospheric research. In contrast to earlier interstellar bodies that traced steeply angled paths across the solar system's fringes, this one slices right through the ecliptic plane, the zone of peak solar wind concentration, magnetic intensity, and space weather vigor. It arrives amid the peak of solar cycle 25, a time when coronal mass ejections surge in number and the sun's magnetic patterns descend into utmost turmoil. Consider comets as innate gauges for magnetism and plasma, drifting probes in the cosmos. Their ion tails offer tangible signs of the unseen magnetic threads woven into the solar wind. Shifts in tail direction, luminosity, and shape disclose details on solar wind velocity, thickness, field orientation, and the transit of shocks or disruptions. For years, experts in space weather have relied on comets within our solar system as distant detectors, deriving precise data on plasma states from telescope views. 3I Atlas could broaden this method to encompass substances with a wholly distinct origin and makeup. Unlike comets from our solar system, which coalesced from the same ancient cloud that birthed our worlds, this outsider bears frozen compounds forged near another sun in a far-off system, perhaps eons in the past. Should coronal ejections influence its actions, we'd be seeing the inaugural recorded clash between our sun's magnetic domain and elements from a foreign stellar realm. The close pass by Mars on October 3rd yields an exceptional vantage that earthly telescopes can't match. ESA's ExoMars Trace Gas Orbiter and NASA's Mars Reconnaissance Orbiter will scrutinize 3I Atlas from spots about 0. 19. AU distant, around 28 million kilometers, granting perspectives and clarity unattainable from ground installations. The Mars Reconnaissance Orbiter's advanced imager, built for sharp surface scans, ought to hit pixel resolutions near 30 kilometers when aimed at the visitor. Though this won't uncover nucleus features, it might differentiate a dense core from a sprawling coma envelope. Even more crucially, synced views from Mars satellites and terrestrial scopes will yield parallax data to refine estimates of the object's dimensions and vigor beyond what solo angles allow. Spectrographic tools on Mars platforms add further insight. The ExoMars Trace Gas Orbiter features analyzers tuned for faint gases in Mars's air, devices that might profile emissions from 3I Atlas at its nearest point. Spotting CN, CO, CO2, or similar molecules would yield straightforward clues to the object's chemistry and how sunlight releases its interstellar frosts. Observatories around the globe are aligning watch efforts via the International Astronomical Union's Minor Planet Center and key astronomical bodies. Their aim is thorough, broad-spectrum surveillance to follow shifts in brilliance, spectral shifts, and structural changes as 3I Atlas reacts to fluctuating solar wind. Amateur observers play a vital role by offering essential data on the environmental factors encountered by the object as it approaches the inner solar system. Information that major professional facilities, which must divide their attention among numerous objectives, are unable to gather on an ongoing basis. Estimates of visual brightness, imaging through CCD devices, and detailed photographs from committed hobbyists deliver the fine-grained time-based data required to spot brief fluctuations, potentially linked to particular solar weather phenomena. Historical examples of intense interactions between coronal mass ejections and comets stem from thorough studies of comets within our own solar system. A prime instance is the Stereo mission's record of Comet Encke's tail separation in 2007, which highlighted the fierce nature of magnetic reconnection involving solar plasma and cometary substances, fully detaching the ion tail in a sequence captured by onboard instruments and interpretable via models of plasma behavior. Should comparable tail-severing incidents happen to 3 Atlas, they might yield groundbreaking understanding of the ways solar magnetic structures engage with material from beyond our system. Variations in the makeup of volatiles from solar system sources versus interstellar ones could lead to distinct patterns of ionization, levels of magnetic linkage, or reconnection behaviors, shedding light on core principles of plasma science in scenarios impossible to replicate in Earth-bound labs. The research inquiries go further than mere solar weather effects. 3I Atlas bears isotopic markers from its originating star system, potentially disclosing details on stellar nucleosynthesis mechanisms, patterns of supernova contributions, and the chemical development across distant galactic regions. The warming from the sun that releases these long-preserved volatiles grants us a pioneering chance to examine interstellar substances through close-up spectroscopy. As the body passes through diverse solar weather zones, from the calm realms of interstellar voids to the heightened turbulence around solar maximum, it presents a real-world test of how cosmic rays and magnetic influences shape interstellar matter across extended periods. Such monitoring could uncover if prolonged exposure to cosmic rays over millions of years has modified the object's chemical makeup, structural integrity, or volatile reserves relative to newly formed comets in our system. Advanced radio astronomy efforts by experts might pick up emissions from molecular lines, exposing details on internal heat distribution, spin speeds, and release mechanisms as sunlight seeps into the core. Techniques involving very long baseline interferometry could discern features in the surrounding envelope, suggesting if the core represents a unified body or a scattered array of minor pieces bound by faint gravitational forces. The schedule for observing 3 Atlas aligns with recent progress in tracking and simulating solar weather, features absent from earlier visits by interstellar objects. Continuous readings of solar wind from various probes, refined magneto-hydrodynamic simulations of ejection spread, and extensive terrestrial observation arrays furnish the backdrop needed to explain shifts in the object's conduct, insights beyond the reach of past astronomers. 3I Atlas could furthermore act as a benchmark for systems designed to protect our planet. Despite presenting no risk of impact with Earth, its path, luminosity changes, development, and reactions to solar conditions enable testing of telescope-based spotting approaches, path calculation methods, and assessment tools critical for handling any dangerous interstellar intruder nearing our world. The wider ramifications of studying such interstellar arrivals reach into astrobiology and the quest for extraterrestrial life. Should 3 Atlas transport organic molecules or prebiotic elements from its home star system, spectral examinations might indicate if the foundational chemicals for such findings indicate that forms of life could be widespread across the galaxy. These revelations would carry deep significance for grasping how intricate biological systems might develop in distant star systems. The extended observation window for the interstellar object lasting into early 2026 allows researchers to pursue in-depth analyses well beyond the thrill of its initial pass by Mars. Its perihelion on October 29th and nearest pass to Earth on December 19th offer several chances for thorough examinations as the comet responds to varying levels of solar radiation. As preparations ramp up for the exceptional viewing windows in October, the alignment of factors, including the interstellar traveler, peak solar activity, cutting-edge detection tools, and global collaborative efforts, holds the promise of breakthroughs that might transform our views on the dynamics between star systems and the vast interstellar medium. The coming months in the calendar could unveil insights that address core inquiries about humanity's position within the larger cosmic landscape. Part 15. Gazing ahead to October and further. Highlight October 3rd, 2025, 21st, and 29th on your schedule. Emphasize December 19th prominently. These milestones could mark pivotal shifts in our knowledge of interstellar objects, their interactions with space weather, and the expansive cosmic environment encircling our solar system. The developments during these specific intervals might resolve long-standing riddles that have intrigued stargazers ever since people began pondering our role amid the stars. On October 3rd, 3I Atlas reaches its nearest point to Mars at 0. 19 astronomical units, about 28 million kilometers from the reddish world. This marks the inaugural instance in human records where an interstellar interloper ventures inside the path of Mars-orbiting probes built to examine minor celestial bodies. NASA's ExoMars Trace Gas Orbiter and Mars Reconnaissance Orbiter have modified their imaging plans to document this historic clash between human engineering and cosmic wanderer. The observational setup from Mars provides perspectives unattainable from ground-based telescopes on Earth. The orbiters will scrutinize 3I Atlas from varied angles, which could clarify uncertainties regarding its dimensions, form, and behavioral patterns that a solitary vantage point fails to resolve. Coordinated sightings from both Mars and Earth might yield parallax data to refine estimates of its range and structural features more accurately than in prior interstellar flybys. Harvard astronomer Avi Loeb's portrayal of the event as a blind date with Mars neatly conveys the blend of anticipation and unpredictability in these studies. The Mars Reconnaissance Orbiter's HiRISE instrument ought to deliver image resolutions around 30 kilometers per pixel when aimed at the visitor. While not sharp enough for surface features, it may still differentiate a dense core from its surrounding hazy envelope. Expectations for scientific yields should stay grounded to prevent letdown upon the release of early data. At distances beyond 1 astronomical unit, interstellar objects typically show up as mere dots even to the strongest Earth telescopes. The probable results include tighter bounds on its scale, luminosity, changes over time, and chemical makeup via spectra, rather than striking close-up views of bizarre formations or surprising occurrences. October 20th and 21st herald a distinct astronomical highlight as Comet C2025 R2. Swan swings to its minimal distance from Earth around Enfurio. 26-0. 27 astronomical units. This aligns ideally with new moon skies free of moonlight disruption and the height of the yearly Orionids meteor display, fostering ideal darkness for tracking the comet. Forecasts for its visibility currently point to Comet Swan hitting a magnitude of 4 to 6 at perihelion. Visible to the unaided eye in clear, dark conditions, this object offers superb sights when viewed with binoculars or modest telescopes. Yet, forecasts for a comet's luminosity involve substantial unpredictability, particularly with recently identified long-period ones on their debut trip toward the inner solar system. The Swan comet might surpass projections in striking ways or leave stargazers underwhelmed should it lack the impressive tail features that render comets so striking to behold. The overlap of various astronomical occurrences in the latter part of October opens up remarkable chances for side-by-side skywatching. Enthusiasts might catch sight of an extrasolar guest, a vivid comet from our solar system, several shooting stars hourly from the Orionids, and ongoing impacts from the height of solar cycle 25, all within prime dark sky windows free of moonlight. On October 29th, 3 Atlas hits its peak exposure to sunlight upon arriving at perihelion, about 1.36 AU from the Sun. This nearest pass by our star could expose the cosmic wanderer to heat that releases frozen materials trapped in its core for eons while traversing the void between stars. Studies around perihelion might show if 3 Atlas adheres to standard comet behavior or shows distinct traits tied to its origins beyond our system. Sunlight could trigger sharp surges in brilliance, impressive tail growth, or breakup incidents that set extrasolar objects apart from those born within the solar system under varied circumstances. At perihelion, 3I Atlas stays beyond Earth's path, more distant from the Sun than our world, yet near enough for thorough Earth-based scrutiny through the end of 2025. Astronomers at global facilities have organized joint efforts to track shifts in luminosity, spectral shifts, and structural changes as the intruder reacts to intense solar radiation. December 19th signals 3I Atlas's nearest point to our planet, around 18 AU, or about 270 million kilometers away. To put it in perspective, that's nearer than Mars at opposition's farthest, yielding top-notch observation prospects for experts and hobbyists alike, using basic scopes across the colder season. The prolonged visibility of 3I Atlas into early 2026 allows research to persist well beyond the buzz from its Mars encounter and perihelion flyby. In contrast to Oumuamua, which sped away from the inner solar system before in-depth analysis, this outsider provides extended periods for close examination as it adapts to fluctuating solar warmth and cosmic weather patterns. Balancing realistic outlooks against exaggerated buzz calls for measured guidance on what the public should anticipate. These icy bodies and extrasolar travelers are famously capricious, capable of thrilling beyond hopes or falling short for those expecting dazzling shows. Probable outcomes include steady luminosity shifts, understated spectral alterations, and form changes best spotted via scopes, not bold naked-eye spectacles for the untrained eye. Expert photos could uncover intricacies in the coma expansion, tail shaping, and reactions to solar wind shifts, though such findings will probably appear as technical insights over eye-catching wonders. Key breakthroughs might come from spectral studies exposing makeup, isotope balances, and gas contents, rather than flashy changes that draw headlines. Vigilance on space weather persists at high levels amid the cresting of solar cycle 25. Through the end of 2025 and into early 2026. The Russell-McLaren influence around the fall equinox period boosts the chances of intense geomagnetic disturbances, which could lead to stunning aurora shows and disruptions to tech infrastructure from space weather. NOAA's Space Weather Prediction Center keeps up non-stop surveillance of solar events using various satellites and earthbound observatories. The ENL model persists in following coronal mass ejections as they travel across the heliosphere, offering predictions on potential solar storm encounters with Earth's magnetosphere, Mars spacecraft, and the path of 3 Atlas. Aurora chasers and space weather fans ought to watch SWPC notifications for G-scale geomagnetic disturbances, solar radiation storms on the scale, and R-scale radio disruptions that might trigger auroras visible farther south than usual during calm periods. The mix of peak solar activity and ideal equinox positioning sets up prime opportunities for striking space weather spectacles across October and November. Monitoring for earthquakes in Venezuela persists as aftershocks develop after the 6, 2, and 6, 3 magnitude quakes from late September. Seismic groups uphold ongoing watch over local quake patterns, although no dependable techniques allow forecasting if bigger quakes could strike the area soon. The intricate plate boundary dynamics between the Caribbean and South American plates guarantee that this zone will keep producing quakes sporadically yet surely across geological eras. Construction standards, disaster readiness plans, and community protection strategies must rely on proven seismic science instead of unproven links to space weather or cosmic occurrences. Observations of novae proceed for V1935 Centauri and V7994 Sagittari alike. As these star blasts progress via their typical fading luminosity stages, experts and hobbyist stargazers globally supply light measurements and spectrum data that uncover the progression of nova mechanics over timeframes, spanning months to years post the starting thermonuclear blast. The American Association of Variable Star Observers oversees these tracking initiatives via uniform guidelines, enabling valid cross-checks of data from diverse watchers with assorted gear. The energetic signals picked up by Fermi and Swift spacecraft keep yielding clues about the particle speeding mechanisms at work in nova shock fronts. Episodes of dust creation could happen in one or both novae in the months ahead, causing brief dimming as fresh tiny grains soak up and redirect the star's glow. Such dust-induced fades, should they take place, would yield extra details on the makeup of nova outflows and the environments within growing remnants of stellar blasts. The narrative we'll craft for October onward hinges on distinguishing solid data from guesswork. Every event from interstellar object motions and space weather dynamics to quake tracking and nova development adheres to proven natural principles that function separately from the seeming bunching of incidents that drew focus in late September. Still, this overlap merits recording and study as a striking instance of the universe's occasional flair for staging vivid happenings in varied realms over tight timelines. If this grouping signals mere chance, hidden ties we haven't grasped, or just the natural outcome of existing in an ever-shifting universe, is a lingering puzzle that further sightings could clarify. The key message for viewers is to savor these sky spectacles securely while holding on to grounded. It is essential to temper our expectations by relying on credible data from trusted institutions instead of hype-driven news coverage or baseless speculation. Organizations such as NASA, ESA, the Minor Planet Center, the United States Geological Survey, and the NOAA Space Weather Prediction Center deliver dependable, regularly refreshed details on current progress. Everyday enthusiasts can play a valuable role in these studies, advancing our grasp of astronomy while directly encountering the awe of celestial happenings. Capturing images of comets, gauging their brightness visually, tracking auroras, and submitting seismic reports via recognized channels enable non-professionals to actively record this extraordinary phase of space-based occurrences. Looming over every aspect of these sightings is the intriguing query of whether this bunching of timings points to more than mere chance. Should this alignment seem uncanny, and it often does to numerous watchers, it might stem from the unusual alignment of our usual distinct timelines for star formation, Earth shifts, sun cycles, and visits from distant objects, a rare alignment seldom seen in a single lifetime. The potential goes further than just October's direct viewings, reaching into subsequent reviews as information from Mars satellites, close sun spectral scans, and prolonged surveillance data rolls in. We will examine precisely what has transpired, steering clear of predictions about potential outcomes and upholding the key divide between raw data collection and its explanation, which underpins sound research practices. Reaching a definitive judgment on this striking overlap could demand several years of meticulous review to distinguish true causal links from random groupings, proven knowledge from untested links, and significant trends from mere mental overlays. Undeniably, we are observing a blend of astronomical incidents that range from starbursts to ground tremors to meetings with far-off travelers. This serves as a nudge that our world exists within a cosmos vastly more vibrant and linked than everyday routines suggest. Any wrap-up ought to recognize the built-in ambiguities in such events, even as it honors humanity's skill in watching, quantifying, and pursuing insight into our role amid a vast expanse that from time to time reveals its power to astonish, motivate, and ground us via the immense breadth of its ceaseless innovation. Ultimately, maybe the true narrative lies not in debating cosmic ties among these happenings, but in the fact that ours is the inaugural era in humankind's timeline, equipped to spot, track, and probe such alignments spanning varied realms of distance and duration. Such a viewpoint lay beyond the reach of every prior society on our planet,